Hello, my name is Audrey Chung and I'm a PhD student at UC Berkeley. Today I will be presenting RAMP-TAO, a protocol that provides stronger transactional guarantees on TAO, and this is joint work done with Facebook. TAO is Facebook's online social graph data store. It underlies the majority of Facebook's products that support varying user behavior, ranging from posting comments to streaming live video. In aggregate, TAO's read-dominant global workload has over 10 billion reads and more than 10 million writes per second. As such, TAO is designed to serve a few simple APIs well at scale. TAO leverages asynchronous replication to ensure high availability and low latency and is eventually consistent by default. In recent years, TAO has seen a growing need for stronger consistency and isolation guarantees, as developers have shifted from accessing TAO directly to using a higher level query framework, which makes it easier to express complex operations on the social graph. A single high level operation generates many sub-requests to TAO, and the lack of stronger guarantees between these requests can lead to anomalies that developers must handle. As an example, consider a hypothetical social media product on TAO that allows musicians like Alice to share their sheet music and recordings in the same post. We want several different types of guarantees to support this functionality. First, without read or write consistency, Alice may not see her new post immediately after creating it. Also, to ensure that either both her sheet music and recording are posted or neither is, we need failure atomicity, the guarantee that ensures all parts of a transaction are either committed or aborted. Finally, we don't want another user like Bob to see only Alice's sheet music or only her recording on her post. We need atomic visibility, which guarantees that all or none of any transaction's updates are visible to other transactions. These are the sorts of guarantees that TAO needs to provide to hide anomalies from product developers. While these may seem like simple guarantees, they are challenging to provide under TAO's workload. First, we need low storage overhead as we deal with petabytes of data each day. Also, given the skewness in our workloads, any solution must be cache-friendly for low latency and for hotspot tolerance. Finally, any additional guarantees should only require the applications that need them to pay the resulting performance and storage overheads. A strawman solution could be to overhaul TAO's replication protocol and enforce these guarantees synchronously. However, this would lead to unacceptably high overheads. Facebook's strategy for strong guarantees has been to layer them on top of the system to retain its reliability and efficiency while not affecting its availability, durability, and replication processes. A system called FlightTracker now provides read-to-write consistency over many data stores including TAO, and more details can be found in the OSDI 2020 paper. For failure atomicity, write transactions using variations of the two-phase locking and two-phase commit protocols have been implemented. Laying atomic visibility on top of TAO remains an open problem and is the focus of this work. However, is atomic visibility actually needed? We perform a measurement study that shows that we require an intuitive read-transaction API to support atomic visibility. Without this guarantee, 1 in every 1,500 naively batched reads violate this property. Furthermore, the rarity of this issue is a source of complexity for developers. These read anomalies are non-deterministic and difficult to detect, reproduce, and investigate. Now I will give an overview of the read atomic multi-partition or RAMP protocols, which are the only algorithms we are aware of that specifically provide atomic visibility. While promising, I will explain why we cannot apply them directly to TAO. The original RAMP protocols involved 3 stages. They first naively read each item, then detect missing versions from potentially concurrent write transactions, and if there are missing versions, fetch them from the database. Say we have a database with 2 objects, x and y, on different shards. Transaction A writes x and y with version 1, while transaction B writes x2 and y2. RAMP writes the entire transactional write set along with each of the keys in a transaction. Here, y2 and its corresponding transactional write set have not yet been updated on shard 2, but x2 is present on shard 1. Let us say we want to read x and y in a transaction. RAMP first reads these 2 items along with their most recent transactional write sets. Here, the database returns x2 and y1 along with their transactional metadata. Next, RAMP uses the write sets to determine if any versions that are needed to satisfy atomic visibility are missing. Here we see that we need to read y2 because x2 and y2 were written together in a transaction. With y2 now fully updated in the database, RAMP then fetches the missing version y2 to return an atomically visible result. Our key observation is that we only need to ensure atomic visibility for recent transactionally updated data. This is because first, data is atomically visible if it was not part of a write transaction. Given that only 3% of current TAO writes are transactional, the vast majority of data is atomically visible by default. Second, once data has been globally replicated under TAO's eventual consistency and no new updates occur, any data we read will satisfy atomic visibility. Thus, as long as data hasn't been updated by write transactions recently, we know it is atomically visible. This insight allows us to minimize performance and memory overheads by keeping limited metadata in a cache to serve the vast majority of reads locally. RAMP-TAO also involves up to 3 stages. It first reads every item from the cache, detects missing versions from potentially concurrent write transactions, and fetches these missing versions by relying on limited multi-versioning in the cache. We will now give several examples of write transactions under RAMP-TAO to share the intuition behind our protocol. Let us say transaction E writes x7 and z7, while transaction F writes x8 and y8. Here, x8 and its corresponding metadata have not yet been updated on shard 1, but y8 is present on shard 2. Note that instead of storing the full transactional write set with each key, we spread the transaction metadata to reduce the database storage overhead. We modify TAO to store limited transactional metadata, including a bit to each item indicating if it was recently modified by a transaction. Note the cache stores the keys as well as the transactional write set for only the past 3 minutes of writes. Now say an application wants to read X and Y in a transaction. We fetch these keys and their corresponding transactional metadata. Using the write sets of transactions E and F, we find we are missing x8 since X and Y were written together in a transaction, and we need to do a second round of reads to obtain this key because our current result does not satisfy atomic visibility. Here, another transaction G occurs, and the cache replica is updated with x8 and x9 along with their transactional write sets. We add limited multi-versioning in the cache so that we can access any versions needed to satisfy atomic visibility. During our second round read in RAMP-TAO, we ask TAO for x8, which is available since we have multi-versioning support, and we're able to return an atomically visible result of x8 and y8. Under RAMP-TAO, most read transactions can take the fast path, which involves only one round trip to the local cache. Items that are not transactionally updated can be served directly from the cache, while old items that were transactionally updated can also be locally served. Here, after 5 minutes, the cache no longer stores any transactional metadata for keys X and Y. However, the write set X9, Y8 satisfies atomic visibility since there are no recent transactional writes to these keys. They can be returned to the client immediately after the first round without any additional checking. We demonstrate that RAMP-TAO can be feasibly deployed in production. The graph on the right shows the request time distribution of our protocol. We can see that RAMP-TAO's 99th percentile latency is comparable to that of TAO's tail latency. Moreover, we find that over 99.9% of read transactions can complete in one round. Finally, RAMP-TAO results in a modest 0.42% increase in memory overhead from storing transactional metadata and supporting multi-versioning, and this has minimal impact on TAO's overall performance. In conclusion, this work has demonstrated how a layered approach to provide stronger consistency and isolation guarantees is effective and prevents these properties from impacting the performance of applications that do not need them. Furthermore, we have shown how to scale RAMP by minimizing the cost of providing strong guarantees by focusing on recent transactionally updated data. Finally, supporting atomic visibility provides a foundation on which we can further strengthen isolation on TAO. Thank you.